All right. So now for something completely different, I think. So I've been asked to talk a bit about some of the improvements we made in 5.1 and the 5.2, and some of the things are on the way into the next release. It will kind of give you a bit of insight on what's under the hood of some of these components. And so I'm going to talk about three different things. The first one is an optimization that we've done to reduce the amount of memory that NSO is using. This might not seem like an issue. It originated from a Config customer who started to get very large memory consumption due to the schema files, or to the YANG modes. They had somewhere in the vicinity of 700-ish YANG files, and they were not even at that point covering the entire possible configuration of the device. So they were getting a bit concerned. And the memory for that was like 200 megs or something. So not very much from an NSO perspective, but on an actual device, it starts to become a problem. Right? So that's when I started to look at this, and about the same time we had one of these technical lab sessions with NSO, and one of the other developers had some problems starting NSO on his laptop because, well, it turned out that the memory wasn't enough. And the reason for that was that they had they had two NEDs loaded. They had Juniper and iOS XR, and that consumed 3 gigs of memory during startup, and his virtual machine just didn't have that. And then it starts to become a problem, right? If you can't run the NSO environment on your laptop, you can't really develop properly, and that was with just two NEDs. And now in NSO 5.1 with CDM, we're actually promoting that you have multiple versions of the same, so it's not the same, but different iterations of the Juniper, for example, or different iterations of XR and whatnot. And we hope that you can use more than 2 different brands. You probably want to use maybe 10 different devices. And then memory starts to become an issue. So as an exercise, I loaded 3 different NEDs on my NSO system: Junos, iOS, and iOS XR. And just the schema for that consumed 1.9 gigs of memory. And that's when the system is up and running. And when you do reload, it will actually consume at least twice as much, since we have both versions of the data modes in memory at the same time. Until we have decided that the newly reloaded packages are okay and we can use them. And the sad part is that a lot of this is seldom used. On a typical device, a user maybe touches 5% of the configuration, right? The rest is just, it has to be there. We don't know what is going to be used, but in practice, at a specific instance, only a few % of the actual schema is used. But it has to be there. And the schemas, if you're an NSO developer, you know that you compile these YANG files into FXS files. And an FXS file, what it contains is essentially a representation of every node in the YANG. So if you have a leaf or a contain or a list, that is represented by a data structure, which we call a CS record. And CS comes from the first iteration of this language, which was called CompSpec in the old days, before YANG was standardized. But it contains the same information as a typical YANG node, a list or leaf or something like that. And when we load these FXS files, which are just a sequence of records like this, we store them in an internal hash table, which is called ETS. We're using Erlang, and the default way of storing things in hash tables is called ETS. And it's just a mapping from the key, which is what we use as a key is a path to the nodes. So if you have a tree, a young tree, the path would be nodes leading down to your container leaf or nest or to this. So it's a unique key, a unique path in your configuration tree down to the node. So when we load one of these files, we sort of populate the hash table, and also we resolve all augmentations that are potentially in the YANG file. So a YANG file may augment another namespace, putting things into another namespace, or a tree, another configuration tree. In addition to the nodes, or not necessarily in addition, but the way we have structured is that we've broken out from the CS record, we've broken out the documentation parts and stored them separately, and also type information is also stored separately. The reason for that is, of course, that the YANG file consists of purely type information, so it has to be stored separately, since other YANG files may refer to those types. They're not necessarily, and also it sort of makes possible reuse between different nodes, so they can refer to the same type. So if we look at one of these CS records, this is what they look like. This is Erlang syntax, but I think it's fairly straightforward. It's just a struct or a record with that has a name. It's called CS, and then it has a whole bunch of. Let's see if I can get this thing working. So these are sort of the top level layer of the record. So it's quite a few items in here to represent a single node in the YANG. And embedded here is the EXS record, which for some historical reason is what we call the type information. And it has an additional amount of data associated with that record. So this is sort of what every node boils down to, and it's easy to realize that this will take some time, or some space to represent. If we break these hash tables down a bit and see what they consist of, we see that the main part of it is the CS records. There are some documentation strings, there are some action definitions which are sort of complementary to the tree, there are some type information and some header information, but the sort of lion part is the CS records. That's where we need to optimize or improve if we're going to shrink the size of this. This is an example of an instance. This is what it may look like. Again, it's Erlang syntax, so it's very straightforward. The type path is, as you see, the path in the tree, but they are stored in reverse order. So in this case, native is a top element, and then there's a container, there's a list, and blah blah blah, it ends up into the address leaf. We also have a hashed representation of the same path. And this is used when we call C code, for example, and we don't want to send strings. We want to have better representation. So we also have sort of a numerical equivalent of the names. We have the namespace in there. We have a hash namespace, which is also used for programmatic or API interactions. We have the type information. You can say this is an IPv4 type. It also has the path embedded in the type, which is kind of interesting. And a lot of fields down here are just not set. And this turns out to be something that we can use. So a lot of the internal nodes turns out to have the same, largely consist of default libraries. This gave me the idea that we could shrink the size and just represent whatever is actually unique for every node. So we changed this to to a different record where we have the key, which is central. That's where we sort of know how to find what this specific node, and then we used a bitmap to represent which fields are actually set. And then in the embedded record here, we stored just the fields that were unique for this, or non-default for this node. And doing this involves then a packing phase to store things in the database or in the hash table, but also an unpacking phase when you're going to read the stuff from the hash table. That will result in some slowdown, so about 50%, so not too bad. It looks something like this. An example of the same thing, I think, more or less. We have the path up here, which is actually not the same path, but similar. We have the map, the bitmap of which fields are actually set, and we have the values of the fields that are actually set, that are non-default. And we did the same kind of trick for the embedded type information in the embedded type record. Also, the key was represented in the embedded record, so we set that up as well, since it was predominant. And that reduces the memory size from 1.9 gig to about 0.8, so a 2.4 improvement. So that was good, but not really good enough. So we thought, what else can we do? And since we're only using a small percentage of the actual schema at any given time, why not use lazy loading? So we only load the parts that we're actually going to use. So we experimented with this. So instead of storing the records in memory, we just stored a smaller thing, the key or the type path that we use for key, and a position in the file. So whenever we're going to use something, we could look at the position in the file, read it from the file, and then store it in memory. So it would essentially be a lazy loaded cache or a cache of the stuff. So all good, except there are some disadvantages of this, of course. We reduce memory to about 550 gig or 550 megs from 55, which is nice. 3.5. Range of 3.5 compared to the unmodified. But the drawback is, of course, that now we need sort of a baking phase. We need to start the system, flush out or resolve all the annotations, and then flush it out on disk, and then lazy load it. So we get slower access, we get somewhat unpredictable memory usage, and we also have this disk or this file to manage, which is a bit of a pain, especially when you do reload, or you would have to read everything into memory, and so the memory would temporarily be very large again. So not very nice. Or you would have to do it offline and then reload it. So not that nice. But when doing this, I came up with I realized that what we were storing on disk was probably, potentially at least, the same thing multiple times, but at different offsets. So I experimented with just keeping track of what I've already written to the file, and instead store a pointer to the first item that I wrote. So if I instead of storing the same CS record a second time in the file, I just say the pointer to the first instance of the same thing. So essentially deduplicating or removing any duplicates or referring to the same thing. And this turns out to be quite interesting. It's only about 3% of the CS records that are unique, if you factor out the key, the path down to the item. That's sort of potentially very interesting. I think there are multiple reasons for this. If you look at conf-d, it's about 10% that are unique. It's still a very, very large number. But for NSO, it's about 3 times more. And I think the reason for this is that the namespace is mounted in 3 different places in the data tree. It's mounted under configuration for a device, it's mounted under the live status for the device, and also under the template part of the device. So you essentially get 3 copies. So it's not unreasonable to think that all these 3 items will be seen as the same. But doing this, it also turns out that the actual CS record, storing the CS records is just a small, tiny amount of memory. So it's not really worth it to store them on disk. We can store them in the same hash table to start with. There's no point of pushing them to disk. So we get an increase of just 50 megs. So this one, seems pointless. But still, a ratio of 3.2 is not really going to make a huge difference. It's good, but it's not really good enough, I think. So then we started to look at what was left. And what we have then is, we have the key, which is the path, and we have these uniquely stored CS records. So if we took a closer look at the path, we realized that there is something interesting going on here. So this is just a small subset of the paths, where the tree is represented by top node, and then we have, in NSO, we have devices, device, the config, and the conf native, blah, blah, blah. And each node in the tree is actually uniquely identified by the last item in the list, and the rest is sort of shared with its parent. So it doesn't really make sense to store the same path all the time. And the reason we did it this way was that it was just natural to start with. We didn't really think about it. We didn't have the reason to consider optimizing this. But when we look at it from this point of view, it seems kind of wasteful. So, what to do instead? We decided to experiment with storing the paths in trees. So this path, DCBA, would be stored as a tree. So this node down here would have the path DCBA, and this node would have FBA, and so on. So we, instead of getting every path represented many times, we just get a tree that has the size of the actual number of nodes, and the space consumed by this will be linear to the number of nodes in the tree. And we let each of these nodes point directly to the CS record that it's uniquely represented. Or actually, when we insert a new entry into the tree, we first look at our hash table to see if this CS record already exists. And if it does, we just point to that existing copy. Otherwise, we insert a new copy in the CS hash table. So that way we get a tree that sort of points to a minimal set of CS records, just the unique ones, and we of course get a hash table on the side to keep track of the unique CS records. So doing that, it starts to get interesting. It turns out that if we do this, we get a ratio of 24. So now it's just 79 megs instead of 1.9 gigs. So then it's certainly worthwhile. And if we also do, so this is actually without doing the trim optimization where we remove all the non-default values. So if you also do the non-default optimization, we get to about 70 minutes. And this is now part of the 501 NSO release and the conf D7.1 release. You can, both in conf D and NSO, you can optionally enable the trimming, which will bring down the size a bit. For conf D, it's probably more interesting. For NSO, a few megs doesn't really matter. There is a bit of a small performance penalty to do the unpacking. It's actually, this is still far faster than the old hash table, but it's the fastest is to do the normal path channel approach, the default NSO. There was something else I can say about this. Right. Yeah, an interesting observation. When we implemented this binary tree search, I was fairly certain that it would be slower than the hash lookup. So before we used this hash tables to hash the key and then look up a record in the hash table and then just refer to the record. But for some reason, or after some experimenting, we realized that the binary tree search was actually faster. It's fairly, for short paths, for the top nodes, it should be faster, right? Since just involves a couple of compares. But also for deep paths, it's even more efficient to use binary search than to hash. And I think the reason for that is that calculating the hash of a long path probably involves transforming every atom into a string and then calculating a checksum over that string, which is probably far more expensive than doing a binary search over some integers, and arrays and integers. And also the binary search is nicely localized in the cache, so it will probably be very fast. Anyway, that's the way it is. So now this is not only far better memory-wise, it's also about 3 times faster than the previous implementation using hash tables. Another thing that we have been working on is a technology that originated in the CLI net, or in the CLI net team. They implemented something they called the TurboParser. I'm sure some of you have been using it. It's now used in a lot of nets, CLI nets. And it's an implementation that largely processes the CLI commands in the Java code in the net and transforms that into sometimes XML that it sends down up to NSO. And that is much faster than using the built-in parser that we originally used. But it has some drawbacks. So we have been working on an implementation, an alternative implementation in Irvine that is native to the same NSO process. So we don't have to do it in the Java process, because the Java process tends to consume a lot of memory. So there are some restrictions on what you can do in the Java. The TurboParser in Java has been improved over time, but we think there are some good advantages to doing this also in the natively in NSO. It can be used for processing the data that comes from the device, of course, similar to what the current TurboParser implementation does, but also when reading configurations in an NSO node, and for also in conf.d for reading and storing large CLI files. If we look at the original CLI parser, it works on a slightly different, it has slightly different objectives when it was written and what we're still going to use this for. It's essentially a top-down breadth first, if you like. It's a top-down in the sense that as long as there are no choice points or no alternatives at any given state, it will be top-down. But as soon as there are non-deterministic alternatives at a level, and they are introduced when you have, for example, a choice or you have a drop node name on a node. At those points, we need to explore multiple paths. And the way the original sort of CI parser does this is that it goes down all the paths and then merges the results to figure out which is the best result. And if there are ambiguities, it reports back up to the end user. So you get nice error reporting. It may say things like, did you mean any of these 3 keywords when you wrote this? Or when you do tab completion, it allows you to fill in all the alternatives or complete all the alternatives. But it's also a bit slow. So if you use this for reading large configuration files, it has some drawbacks. So the way it works is like that. So the TurboSay is written with a different objective. It needs to be, or tries to be as fast as possible, and it does a pure depth first. And it's sort of stack-based, so it will explore a path, and if it finds a hit, if it manages to successfully parse the command line using that path, it will take that path. It won't try to report ambiguities or anything like that. And it doesn't even keep track of all the information needed to do a proper error reporting. But it makes it a lot faster. So it can be viewed as, when it parses this kind of command line, it will build up a stack of potential alternatives at every level. But if it hits a successful parsing, it will just throw away everything else and not even try to backtrack to any other ones. And when we run this on a bunch of different configuration files, we, depending on what the configuration looks like, if there are a lot of choice points, or choice points, by that I mean drop-node name annotations, it will be faster. So these two, or actually these 3, we get about 10 times faster than the original CLI. Whereas other ones are, we've seen ranges in that area between 4 and maybe 10, 15, something like that. Times faster, which is fairly significant. This is released as an experimental implementation in 7.2, I think. So we haven't, it's still not completely bug-free in terms of being equivalent to the original CLI post. So we have some quirks to work out, but it's still very, very close to being complete. Finally, we have worked on something that has been asked for a very long time in different settings, both in conf and in NSO. And that's the ability for a data provider to do some filtering on the data it reports back to NSO. So if we are integrating with an external database, for example, or a device that has a lot of data, stats data, for example, it could be routes on the device, or it could be some other information that we have. The way we currently do is that the device essentially has to send everything up to NSO, and then NSO will do the filtering. and that is, of course, very slow if there is a large amount of data. So by putting it or allowing the data provider to consume a filter, the data provider can do some filtering before actually getting the data. And that avoids round trip between NSO and the data provider. And it also allows for some XPath evaluation on the actual data provider, which is also good for example, validating configurations or run. XPaths are run in a number of situations, both for when and must expressions, but also for leaf refs, for example, to validate new configurations that has leaf refs in them. So we have added this feature to the data provider API, but also internally to the CDB API. So CDB can now consume some of these filters. For example, provided we have a data model that looks like this, a list foo that has a name and value, and there is some other list that has also name and value, but in addition it has a reference to the value of this list. So not the key of this list, but the value. Then we can do a number of things. We can, for example, in XPath say that we want to see all the foo instances where the value starts with 42 or where the name starts with ETH minus. Now we can push this filter down to the data provider, and it can report back up just instances that match. So if you have millions and millions of instances, that will be potentially much faster. Especially if you can provide this kind of filter to your database, that your external database, then you can probably do something interesting with it. In netconf, the same query or a similar query would be to ask for all the instances that have value 42, for example. You can't do larger than in netconf. In this CLI, you would do something like this: show all instances starting with ETH minus star. Then you can actually combine these on the same command line if you like. So you get all the ETH star instances that also has a value 42 or has a value 42. But you also get an interesting optimization if you look at validation of the database. So if you have a huge configuration, say 10,000 foo instances, and you just delete a single bar instance, all the foo instances will be re-evaluated to make sure that there is, or actually, it's the other way around. If you delete the foo instance, you have to make sure that there are no bar instances referring to that foo instance. It has a default to that one. So you have to walk all the bar instances to make sure there is nothing referring to that missing instance. So instead, if you can send down a filter to the iterator of the bar or the foo instance, saying that let me know if there are any references to value 42, then that would be much faster. So this is what the flow looks like. There is some show operation. NSO gets it. It invokes what we call the getNext callback, which is what you provide in a data provider and sort of iterator. It gets a filter together with this callback that it can store, and then return all the matching instances. But it has an option. You can say that I'm returning all the instances that precisely match this, or I'm returning a superset of the instances that match. So NSO is still prepared to do some filtering if it turns out then it's easier. If the data provider can't handle the entire filter, maybe you can handle a subset of the filters. So part of the filter can do some filtering and then report back. Currently, the filter syntax is, but I shouldn't say it's limited, but it has support for the following parts. So you can do some OR and expressions, not compare. You can invoke some function, you can do exist. So you can't do particularly deep operations, and you can't do very advanced operations, but yeah, so this is what it is. And the speed up you can get from this is, in one way, we're changing the way the algorithm or the complexity of the algorithm. So it could be almost anything. In the particular validate case, we're not really changing the complexity, but we're pushing the list traversal down into the data provider, so we just skip the round trips, and then we get a speed of about 15 for those kind of operations, which might be significant. And as I said, XPath relations are used in a lot of places, not least when we calculate the diffs to send down to the device, especially the CLI diffs that rely on XPaths to figure out the ordering between different operations to send. We are releasing some of this, which actually released in 5.1. And now upcoming 5.2 has some more. We are still working on the CLI engineering, the live status implementation of this. Why we will get there. It should speed up things considerably. As it is now, it's not really feasible to read large amounts of data through the net. So that's about it.
Questions? Maybe.
Questions.
Hi, from Holdback. I have at least 3 questions, but just so all of this looks really nice. Are there any plans for being able to do parallel RPCs towards devices? This is the slowest thing I got right now.
Parallel, you mean parallel action invocations?
Yeah. So I have to collect root information from like 3,000 BTP sessions across 25 devices.
So the short answer is no, there are no plans. But I wasn't even aware of the requirement. But I guess we do parallel RPCs, but only when we do configuration or synchron or those kind of operations, not when they shoot through some other, up through the CLI or specific action invocations. But it's worth thinking about. It probably wouldn't be that hard to implement, I think.
The second is the last thing you had with the filter thing. We have some create code in where we play a lot of ping pong between the programming language and so we create a lot of when you create lists, very long lists, for instance.
Right.
Send them. Is that something that's speed up here? We have a hack, but it's sort of missed.
So you're asking if the creating list instances would be sped up?
Yeah.
Yeah. No, I don't think so.
So the last thing is for the lazy loading. It seems like you could just use it up there and
Yeah. Yeah.
There might be some details, but it's a suggestion.
Yeah. So the reason we didn't really explore that was that the gain wasn't that much in the end. So the space used by the sys records wasn't really that much. And for sure, using a memory map would have sort of worked. But it also adds complexity, so I'm not sure it's worth it. But also, the trick with that is that, or the problem with this, that we need to have them loaded when we do a patch reload, for example. We need to have them in memory to do that, to resolve all the possible mutations and stuff. So it's a bit of a hassle. That's what we do when we share the data model with C code, for example, when we use memory.
We have a question down here. Are there any plans on enabling some type of cascade delete action where you actually go and delete the things, the prerequisites for having a record in place, following when statements and with the command deleting the prerequisites for them? In database, you generally have a cascade delete function you can enable on a table for when you want to be able to have the data still valid after, but to delete the stuff on the other end of the reference.
Right. So when do you think that would be used in this context? I'm not sure I understand the use case here.
I was just wondering, for instance, if you want to remove a large set of data and you want to make sure that your model is still valid afterwards, and you would like to have the links followed and validated, so you can see, like for a dry run of a remove, you see that all of these things would be removed if I had that act upon the relationship and remove the things that made that data need to be there.
Right. Yeah, so what we do, the thing is that what we do internally is to keep track of those relationships. It's just that for certain relations, like the one I showed here, we are not, if the relief ref is to an actual list instance, then we would keep track of it, and it would be fast. But since the reference was to a leaf, any leaf inside that instance, that would have the value 42. It could be multiple instances that have the value 42. So that complicates things a bit. And those sort of dependencies we don't keep track of. I'm not sure. Maybe we could use some technology like you're talking about, but I haven't really explored it.
Thank you.
Sure.
Hi.
Hi.
How do you feel? I mean, we are able to use Python for all sorts of things.
Yes.
And maybe in the process of discovery before the reconciliation, we're not sure, when we're trying to set up a standard for for a model of service, we're not sure what kind of cases we have that can be used, and maybe we have some more corner cases. We're not sure where is the limit, and maybe we would like to have a quick scan or something like that to see whether our thoughts are right on the right place.
Mm-hmm.
How do you feel about multi-threading in Python itself? If you need a live exec command for, I don't know, in 1,000 devices, and you need a short answer of the state of those interfaces, whatever, it doesn't matter. How do you feel about that? Is it a good practice? No? Maybe once just to see it, or maybe you have a better idea?
Yeah, well, I don't really have an opinion, to be frank.
Okay, honest enough.
With, yeah, I don't know.
What would you do if you have such a problem?
I would look at the code and see what I could do. I think I understand the need for having multiple concurrent RPCs in that way, especially when you are. So what we recommend in the brownfield deployment, right, is that you instead of doing sync from all the time, you use live actions to explore the current content of the devices. But if you have that approach, you end up with situations where you may want to run multiple concurrent live actions, for sure. So that's something that we should look into. Yes, I haven't encountered that issue before. If you have a few devices that you interrogate, then it's fine. But if you have thousands, like you said, it's going to be slow.
Thank you.
So, a couple things here. First of all, what data structure do you use for storing leaflets? Like for the Holdback, you explained that you have the binary tree.
Yeah. But
what do you use for storing leaflet elements? How do you build that one?
So in leafref, typically a leafref refers to a specific list. So we don't need to store the path to that specific list. We only need to store the name of the instance that we're referring to. So that the data structure is just a simple integer or item that we store in the database. So it's very efficient.
The next part is the filtration system that you showed, the validation. Can that also be applied to the leaflets then?
Yeah, it is, yes.
Okay.
Yes. I think it's, that part I think has already sort of been optimized in the previous implementation. I don't think it actually requires the list. Well, it depends. So if you have a situation where you have multiple keys and you have references to individual parts of that key, then I think the filters will be applicable. But typically you only have a single element as a list key, and then we can do a simple exist lookup. We don't actually need the filters for it.
Yeah, sorry, maybe I missed this part. According to what you said, the behavior before NSO 5.1, I noticed that not only for the iOS net, if you have any other net installed, actually, for example, WSA, ASA, iOS is net installed, the package reload will actually taking a lot of times.
Yeah.
So with this enhancement, we're saying in NSO 5.1, it should be ideally reduced, right?
Right. So this particular enhancement does not affect that.
Okay.
There are some other things that fixes that we made that solves part of that problem. And one issue that we discovered fairly recently was that if you have your packages stored as gzip tar files, then that is extremely slow. Just a fix that can be used for existing systems is just to unzip them. So you have just tar files, or even unpack the tar file. If you do any of those things, it will be much faster than loading a large zip file, and that's just because the uncompressed implementation that we used was very slow. We used them built into the package. Now we have optimized that, so in 7.01 and then later, the last release is 7.01 and then 7.02, and also any release of the old versions, we have a faster reload of zip packages. But we're also looking at what we can do for the general reload speeds, because there are other things that are also slow. But that's something we're working on.
Okay. Thank you.
Yes. Thank you. So just one last thing. So you mentioned that we can do filtering using the RIP API. We can do it through CLI. Can we also do it in templates, like device templates or service templates, any of those?
Yes, I'm not exactly sure. If you have a filter in the template in Express as an XPath expression, for example, yeah, as long as the data provider and its CDB in this case understand the type of filter it will be applied.
Okay, thank you.
I was interested in the new parser for the Cisco CLI.
Sorry?
Just to confirm my understanding that this improvement will be visible, for example, in sync formation.
So eventually it will be. I think the current depending on which net you're using, currently it's if it's a Cisco net, for example, it's using the Java version of that technology. But if you but I'm not exactly sure which ones are using. I think a lot of the nets, these CLI nets these days, use a Java version of that. What the TurboParser does is it allows you to load things, large configuration files, into the NSO CLI, for example. It's now available as an explicit command in the CLI. I think it's hidden in the DevTools group, so you can use that. The intention in this release is to release it so it can be evaluated and check whether it actually covers everything that we want it to cover. So we're releasing it to customers to try out, to verify, and then we're going to move it into the nets eventually. That's it.
Okay, because we are also doing some tests a few weeks ago. And for example, with the Juniper net, I saw that I was trying to sync from, and I was adding in partial sync tree to synchronize routing instances, and I was taking one production box, and I saw that, for example, to sync something around 1,400 routing instances means for us penalty like 150 seconds, which is too much for us. So do you have any idea how we could improve this? We are using NSO 4.6.2 for the net version. I'm not sure,
but that's a net confident, right?
Yes.
No, I don't know. We have to ask some other developers about any takers here. No. You have to grab some of us. That's not really my area of expertise, I'm afraid.
Okay, thank you.
All right, I think we need to break here. So thank you, Johan.
Cisco, the bridge to possible.